Today we'll be discussing the questions from the Leetcode weekly contest 322, and the question that we are going to be discussing is minimum score of a path between two cities. And the question statement given is you are given a positive integer n representing n cities numbered from 1 to n. You are also given a 2D array roads where roads of I is equals to a of I, b of I, distance of I. That means there is an edge between A of I to B of I, and it is a bidirectional edge. And what does a bidirectional edge mean? That means that if A of I, that is, let's just say there are two numbers or two nodes, 1 to 2. So there is a road between both of them. Okay. And the distance to go between them is distance of I, that is already given there. And they have said you have been given a array of list such that these roads are present there, and the graph has been given to you, and you need to say what's the minimum distance to go from 1 to n. Okay. And how have they defined the distance as? Let's understand with this example. So they have said there are four nodes. Okay, so you need to go from 1 to 4 somehow, and the distance they have said is nothing but you have to take some path. So how are we going to take that path? Let's just say we are going from 1 to 4. We can just directly jump from 1 to 4 directly here. And what will be the distance? The distance will be 7 only. Now let's understand with this distance right here. Now if we take this path right here, 1 2 and 3, 1 2 and 3, then we go again back to 2, then we go to 4 again. Now we can do such iterations also. That means we can visit a node twice also. That is perfectly fine according to the question that is given here. So what is the distance here? They have said the total distance that you took to reach 4 will be the minimum of all the distances in this path, and that is nothing but minimum of 9, 6 and 5. What is it? And the least possible value that is present here is 5. So that is why the distance here is 5. Okay. And they have also mentioned that there can be two disconnected graph also. That means, so if there is 1 2 3 and 4, let's just say we make this to 6. Okay. And somewhere here this 4 becomes 6 here. So there can be some nodes also like 5 and 6. There is a graph which is 5 and 6 like this also somewhere present there, but we do not need to take care of this part because we are only considered for the path 1 to 6. Okay. And mind you, it is not necessary that you will take a path of like 1 2 3 4 5 and then only you'll go to 6. You can take any path like 1 to 6 and 1 to 4, 1 to directly 6. Okay. Any path is possible, and they have said that it is guaranteed that there is always a path. Now let's understand it with this example and we'll be good to go for the code and explanation part. So for here, they have said again 4, and what is the path that we can take? If we go directly here, we can just get a minimum of 2. But what if we go from here to 1 to 3, then 3 to 4? First, let's just say we are going jumping on from 1 to 4, then again to 1, and then we are going to 2. What is the path that we are taking again here? Again, if we see, we are taking 2 only. Why so? Let's see. We jumped on from 1 to 3, right? And what was the distance that we took? That is nothing but 4. Now after that we jumped from 3 to 1 again, right? So again we'll take a distance of 4. Is the same thing, so it doesn't matter to write the same thing twice. Now from 1 we'll be saying we can jump to 2. Now that is nothing but a distance of 2, and what is the minimum? It is again 2, but we can just simply jump on from 1 to 2, right? And we can get the minimum distance. That is the case. But when is the case when this such thing can happen? Let's just say uh, this is something like a 20, fine, and you need to reach the node 4 somewhere like this. And after that, let's just say this node is not directly connected right here, and this is connected somewhere like this. Then what do you have to do? Then you have to take the whole path. You cannot just stop at the time you just find the last node. That means, let's just say we need to reach 4, right? So will I just stop at node 4? I'm just taking this path 1, 3, and 4, and I reached 4. Can you just stop there? No. If you just stop here, what will be the distance? The distance will come out to be 4. But let's just remove this part also, and let's just say the distance here is 1. Fine. And there is no node right here. So what is the distance to reach this 4? If we are not visiting 2, it is 4. But what if we visit the node 4 once, and then again we go to node 2, and then again we come back to node 4? Then the distance will come as to be 1, right? So again I'll be explaining this. So this is a very important concept that we need to understand, otherwise we'll not be able to do this question. So let's just say this node is not here, and the distance for this is 1. What are we going to do? We are not just going to stop when we find 4. We are still going to search for a better answer or a better minimum distance. Okay, so you have to still find for a better minimum distance, and we see that we can actually find a better minimum distance by going to the right once again, and we find 1. So that is what we are going to return. And this question basically holds sums up to something like, you start from 1, you travel to each of its node, and whatever is the minimum, you have to just give me that. That is the whole point of this question, okay, what it's trying to tell you. And let's just say you have this one connected component, right? You have to find the minimum of the whole connected component, and there, let's just say there is something like 5 and 6, and there is even a lesser minimum here, like let's just say 1. But you cannot just take this thing. Why? Because this is not a part of this connected component right here. We are just concerned about a path from 1 to 4, and not anything including other than 1 to 4. Okay, so this is what you have to find. You just go to the part for the path of 1 to 4, and you find what is the minimum distance that you can find, and whatever it is, you just return that. Okay, so and how to do this? I've used BFS here to do this question. So how to do this, let's just see. And we'll be using Dijkstra's algorithm, and if you don't know Dijkstra's algorithm, please do check that out first. Okay, it will be much easier. The whole thing is just the copy paste of Dijkstra's algorithm, and only one line is being changed here, fine, and nothing else is there. But if you don't know, I'll just give you, or if you have forgotten, I'll just give you a quick summary of it. Let's just say that if you can reach the node 1 to 3 by a distance of 4. Okay, and there is one more thing, such thing like this. So what are we going to do in Dijkstra says that I want to reach from 1 to 3 by a shortest path, right? Dijkstra's will do a what? It will do a BFS on the queue, and let's just say this is my distance array. So 1, 2, and 3. First one will go to 3 and 2. Okay, in BFS, I hope you know BFS, and BFS is required in this, the way I have implemented it. So from 1 to 3, what is the distance required? It is nothing but 4. So we update the distance array by 4, and mind you, this is the Dijkstra's algorithm, okay, if you have forgotten. So that is why I'm just recapping it, and quickly we'll move on to the code part, how to do it. So this is the distance 4. Now one says, okay, I can go to 2 even. So let's just go to 2. And what is the distance? The distance is nothing but 2. Now 2 says, okay, I can also go to 3 now, right? 2 can also say that, okay, 2 can go to 3. Now 2 takes what distance to go to 3? And it's nothing but 2 plus 1. Why 2 plus 1? Because in order to reach 3, I'll have to first reach 2. And what distance did I take, or what amount did I take to reach 2? It was previously 2. And to reach 3, what extra am I going to take? Nothing but 1, right? So which will be equals to 3. So to reach node 3, I'll be requiring 3 units, right? 3 units. And I see that previously I was requiring 4 units, but now I require 3 units only. So why not just take this path, that is 1, 2, and 3 path? So this is what Dijkstra does. Okay, so this was the recap of Dijkstra's algorithm. Now let's get on to the implementation part. It is a very classical implementation, nothing too fancy, just the plain old BFS that we used to write. So I've created an adjacency list here. There is a bidirectional edge. Okay, bidirectional edge I have already explained you while explaining it. After that, I've just created a priority queue, min priority queue right here, that we use in Dijkstra's algorithm. After that, I've created a distance array and a visited array. And here I'm saying that, okay, if when I'm not there, I'll just go into the priority queue. This is a plain old BFS that we do. So at first, what do we do in BFS? We push where we are starting from, right? So let's just say if we are starting from here, what are we going to do in BFS? First, we push 1 into the queue. Now, 1 will do what? It will visit 2 and 3 simultaneously. Why so? Because this is a BFS. BFS does a level wise traversal. So, that is what's happening right here. After that, when we visit the first node, what do? We just say that, okay, you have been marked visited. I'm not going to come to you again. So, the thing is, let's just say 1, 2, and 3. If you're just coming from here, if you're just coming from here, right, you have already visited this one. Why do you need to visit this again? And this priority queue is already going to take care of that part, but I've still taken a visited array. Okay. And that is the thing about this. After that, what do we do here? And if you just see the Dijkstra's implementation, you'll find the whole thing is similar, except I've just added this part. Even if you don't add, it doesn't matter. Okay. And this part is changed. The only thing in Dijkstra is what I explained you, that we just say that, okay, when I'm coming to a node, okay, what is the node's distance? When I'm coming to a node, I will say that, okay, what was the previous minimum you found and the current minimum you are finding. Let's understand this properly. Right here, I'll just 1 4 and 2 3, I'll just draw a new graph right here just to explain this better. 1 4 2, and let's just say this is 3. Fine. And the distances are, let's just say 4, 5, and something like a 2. So what are we going to do? What is this part doing? This is the most important part, and if you just understand this, it is very 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 easy. Okay. So what does this distance array do? And let's just say we are maintaining a distance array. Okay, something like a distance array, which will say, okay, this is 1 2 3 and 4. This is my array right here. Fine. And these will be the values of those. So at 1, what are we going to require? You're already starting from 1, so the distance required to reach 1 will be 0, since you're starting from the 0 only. So you can just initialize it with int max also. Okay, I've initialized here 0 because there's no space. So after that, what can we do? We can go to 2 or we can go to 4. I'm telling you that you need to go to 3. Let's just tweak this question to, you want to reach to 3. Okay, for just this question. But in the actual question, you have to reach 4 only. But let's just say here we are going to reach 3. We want to reach 3. What are we going to do? One says, okay, 1 will go to 4. Fine. And 4 and we can reach 4 by how much distance? We'll take a distance of 4 right here. Fine. That is perfectly fine. And after that, one can reach to 2 by distance of how much? By 2. So that is also fine. We have reached these things. Now in our queue, what will be there? There will be 4 and 2. Now 4 can reach to some nodes. Obviously it can reach to some node, that is nothing but 3. So 4 is saying that, okay, I will reach 3. And what will be the distance that it will take? I'll write 5. Will I write 5? Obviously no. And let's just see why. Because see, when we are reaching 5, we are reaching through this 4, right? And what is the definition of the distance that is present right here? The definition of distance that is provided in the question, they have said, in order to reach a node, you have to take the minimum of all the elements in its path, right? So that is why the distance to reach 3 will be here as 4 and not 5. Fine. So that is one of the things right here we need to notice. After that, now coming on to the next part. So 2 4 and 4, this was taken as the distance. Fine. Now what if I say that I will go from 1 to 2, since it is a bidirectional, and from 2 I can go to 4 and then 3. This is also possible, right? This is also possible. So that is why all you need to do is, when you are returning your answer, you just need to return the minimum distance that is needed to reach any node. I'll rephrase that again. The minimum distance that is needed in order to reach a particular node. So in order to reach 2, what are you going to need? You are just going to need the distance 2, right? And in order to reach 3, what are you going to need? Minimum distance of 4. If we are just coming from 1, 4 and 3, if I am not coming from 1 to 2 and then again going back, then I'll be requiring 2. But since I'm saying I will only go from 1, 4 and 3, what is the minimum in this path? It is nothing but 4. But if I say that okay, I'll visit 1 and 2, then I'll again come to 3, that is when I'll be getting this 2. Fine. So this is the whole procedure, and at the end of the day, when we are coming here, right, what are we doing? We're just updating the distance array by whatever the minimum distance that we are finding. If we are finding one minimum distance, then only we will update it and we'll push it into our queue, and at the end of the day we'll just print out the minimum number or minimum distance in the overall distance array. Fine. So this is the whole walkthrough of this one, but if you still have any doubt, you can ask me in the comments. Perfectly fine. Okay. And yeah, this is it for this one. And the code will be in the description if you want it, and if you did like it, please do like and subscribe. And yeah, thank you.